Welcome to this explainer. I'm so thrilled you're here because today we're exploring a fascinating evolutionary history that is literally hiding right at the ends of your arms. We usually think of walking upright as the defining human trait. But as we're going to see, the story of how we actually got here is a whole lot more complicated, and it's written right into our bones. Let's dive in.
Okay, I want you to do something for me real quick. Hold up your hand. Take a good look at your wrist. Flex it back and forth, maybe rotate it around in a circle. Curl your fingers into a tight fist. What you're doing right there, effortlessly, without even thinking about it, is actually the product of millions of years of evolution. And it perfectly sets up the central mystery we're unpacking today. What exactly is hiding inside that joint? Well, the first thing to know is that your wrist isn't just some simple hinge. It's actually packed with 8 small, highly intricate interlocking bones. It's kind of like a masterfully engineered puzzle. And this complex geometry is exactly what allows us to pull off our most delicate, uniquely human tasks. I mean, these 8 bones give a surgeon the raw precision to suture a tiny wound, a musician the dexterity to nail a complex piano chord, or even just a kid the coordination to tie their shoes. But here's the twist. Think about our modern human dexterity, playing that piano, tying those shoes, versus our ancient primate origins. A major new study in the Proceedings of the Royal Society B suggests that hidden right inside the geometry of those 8 little bones is the ghost of a much older posture. The research is telling us that our wrists carry the physical memory of a time when our ancestors didn't walk upright at all. Instead, they moved through the world on all fours, resting their weight right on their knuckles. Section 1. The investigation, solving a Paleolithic puzzle. You see, historically, studying the wrist has been incredibly difficult. To really appreciate the challenge here, we have to look at paleoanthropology, the scientific study of human fossils to map out our evolution. For a long time now, paleoanthropologists have been locked in this massive debate. They've been trying to figure out what our ancestors' locomotion looked like before we evolved bipedalism, walking on 2 legs. Did we evolve from knuckle-walking apes, kind of like modern chimps and gorillas? Or did we evolve from a more generalized tree climber that skipped the knuckle-walking phase entirely? The wrist should be the absolute perfect place to look for clues, right? Because different movements put very different mechanical demands on the joint. Just think about knuckle walkers. They don't bend their wrist backward when they move. Upright walkers, like us, actually share that exact trait. Then on the flip side, you have flat palm walkers. Think macaques and capuchin monkeys. They load their wrist in extension. They bend it backward with every single stride. And over millions of years, those mechanical pressures leave permanent physical marks, subtle grooves, ridges, tiny changes in surface geometry. But here's the catch. Remember those 8 interlocking bones? Previous studies usually only looked at 1 or 2 of them at a time. That's honestly like trying to understand how a car engine works by looking at a single spark plug. Enter Laura Hunter, a paleoanthropologist at the University of Chicago. She and her team set out to solve this puzzle by finally looking at the whole picture. And the scope of this is just wild. Take a look at this number, 2,037. That is the number of individual primate wrist bones they scanned. It's literally the most comprehensive analysis of primate wrist bones ever conducted, pulling from living and extinct species, monkeys, apes, hominins, the whole shebang. And this wasn't just a massive study. It was incredibly rigorous. Let's quickly walk through their 4-step methodology. First off, they used CT and 3D laser surface scanning on all of those bones. Second, they took that data and created high-resolution digital 3D models. Third, they used those models to precisely quantify the really subtle surface features that reveal how a wrist bears weight. And finally, they cross-checked their visual observations against heavy computational data. This double verification process, it gives their findings absolute top-tier scientific credibility. Okay, so what did they actually find? Well, the results were overwhelmingly consistent. Across nearly every single bone they looked at, human wrists bear a striking resemblance to those of gorillas and chimpanzees. Not monkeys, not other apes. Specifically, the great apes that knuckle walk. And this wasn't just some isolated quirk in one region of the wrist. It held true across the board. It heavily supports the idea that our lineage used to move exactly like a chimpanzee does today. Section 2. Evolution's Great Repurposing. Now, obviously, we don't walk on our knuckles anymore, so why do our wrists still look like we do? To answer that, we need to look at a very specific anatomical feature from the study. Over on the thumb side of your wrist, there's a fusion of 2 bones, the scaphoid and the central. In knuckle-walking apes, this fusion is a real game changer. It stabilizes the wrist when they're dropping all their body weight onto their hands to move around. Humans have this exact same fusion, but why? Why would we hang on to a stabilizing feature for a movement we literally haven't used in millions of years?
Laura Hunter's explanation for this is just so elegant. It all comes down to a concept called evolutionary co-optation. Basically, this is when a biological structure that evolved for one specific job gets repurposed for something entirely different. Evolution didn't just throw away the knuckle-walking features, it recycled them. The stabilizing architecture that once studied our ancestors' wrists on the forest floor actually became the structural foundation for our extraordinary human dexterity today. It was built for one world and then totally adapted for another. It's exactly like how the bones in our inner ear evolved from ancient reptilian jawbones, or how feathers evolved on dinosaurs that couldn't even fly yet.
Section 3. The tool timeline twist. Now, when you dig into the fossil record, the timeline of this whole evolutionary repurposing throws a bit of a curveball. Simple stone tools first show up over 3 million years ago, made by Australopithecus, which is the genus of the famous fossil Lucy. Then, by 2 million years ago, early members of our own Homo genus were regularly napping tools. But the specific suite of anatomical wrist changes that give us our modern, sophisticated tool-making ability, those only became consistent around 550,000 years ago, popping up in both modern humans and Neanderthals. Let that sink in for a second. Look at that massive lag. Our ancestors were hacking away, making stone tools for over 2.5 million years with wrists that weren't even fully optimized for the job yet. And honestly, this perfectly illustrates a core truth about how evolution really works. As the study points out, our ancestors didn't simply develop the right wrist and then decide to start making tools. The relationship between our anatomy and our behavior just isn't a neat, straight line. The capacity to use tools likely developed right alongside these gradual anatomical tweaks. Actually, scratch that. It's more like using tools for millions of years with unoptimized hands might have been the very pressure that drove the evolution of the wrists we have right now.
Section 4. Healthy scientific skepticism.
Now, of course, as with any major scientific study, there is an ongoing conversation. And this explainer wouldn't be complete without looking at some fair challenges from other experts. Take Philip Reno, a developmental biologist at Penn State. He raises a pretty solid methodological point. He notes that humans and African apes are genetically extremely close, so showing morphological similarity with our closest living relatives might just be the null hypothesis. In other words, our wrists might look alike simply because we're close genetic cousins, rather than it being definitive slam-dunk proof that our ancestors shared a knuckle-walking style. Then you have paleoanthropologist Scott Simpson, who points out a pretty notable missing piece of the puzzle. He brings up the absence of Ardipithecus ramidus in the study's dataset. If you're not familiar, Ardipithecus is a 4.4 million-year-old hominin, and its preserved hand bones showed zero clear signs of knuckle walking. For some researchers, that absence is a big deal because it leaves the door open to the idea that bipedalism could have evolved from a generalized tree climber, totally bypassing the knuckle-walking phase. So, what do we make of these critiques? Well, Hunter's team fully acknowledges them. Paleoanthropology rarely hands you a clean, perfectly wrapped answer. This study isn't claiming to be the absolute, undisputed final word on human origins. Rather, it's a massive, meticulously constructed data point added to a highly dynamic, ongoing debate. And honestly, that's exactly how rigorous healthy science is supposed to function. Section 5. Why this matters today. At this point, you might be thinking, okay, cool, but why should I care about some ancient ape's wrist bones today? Let's bring this right back to you and your modern life. Understanding our origins has some deeply practical applications. Knowing exactly how our joints evolved helps us understand our own biology, like why certain joints are prone to failure or injury under specific conditions today. It reveals why certain anatomical features that seem totally vestigial or useless actually serve critical structural functions. It even helps us understand how a human fetus develops in the womb. And on a more profound level, it explains why our closest animal relatives move and behave the way they do, which just deeply connects us to the wider natural world. If there's one core takeaway I want you to grab from this explainer, it's this. Evolution does not erase the past. It builds on it. The exact same risk that a surgeon uses to save a life or that a toddler uses to learn how to color, they still carry the encoded physical memory of an ancestor moving on all fours through an ancient African forest. The past is literally right there inside of us. So where do the researchers go from here? Moving forward, the team wants to map specific wrist movements directly to specific tool behaviors, trying to pinpoint exactly when and why each little adaptation showed up. They're also gearing up to use some advanced new imaging tech to analyze incredibly fragile early hominin fossils, like that missing Ardipithecus we talked about, which will hopefully fill in the lingering gaps of this giant puzzle. Which leaves us with this final thought. Go ahead, look at your hand one more time. If the 8 tiny bones in your wrist are carrying the ghosts of our knuckle-walking ancestors, what other evolutionary memories do you think are hiding inside your body right now? Thanks so much for joining me for this explainer. Keep questioning the incredible science right in front of you.